today's webinar for you, sizing photovoltaic systems in the latest version of SAM. So before we get started, just a couple of administrative announcements. Probably most of you are aware this is the latest webinar in the series that we are giving this year in 2017. We have one more in September that will talk about the SAM open source project. And all of these webinars can be registered for on the SAM webinars page. And you can also view recordings of past webinars, which is also a reminder that we are going to be recording this webinar, and we will be posting a recording of it after we finish it. Back to the administrative part, if you have questions, there's a questions box in the webinar, the GoToWebinar interface, so you can type questions in there. And I have some of my colleagues standing by, monitoring, ready to answer your questions, and they can interject if one of them seems like it's particularly relevant to what I'm talking about, and otherwise we will leave some time at the end for questions as well. I'll plan not to take the whole hour. So, as most of you probably guessed, this webinar is about various PV sizing considerations. So I'll start with an overview of what those considerations are, and then I'll go into a little bit more depth on some of those considerations and some of the capabilities we have to help with those sizing considerations. I will also be sure to touch on a couple of features that we frequently get questions about, including how to model microinverters and DC optimizers, in addition to your central or string inverters, how to take a look at multiple subarrays, and then a brief venture into the actual physical sizing of a PV system as well, before I wrap up with sort of what the limitations of SAM are in this area, and then we'll have some time for questions. So the maybe sort of daunting introduction is that PV sizing is a pretty complicated problem, and this is a sort of a rough attempt to at least explain a handful of the factors that go into it. I think I've mostly covered them here. Selecting the ideal size for your PV system, if you are looking at a behind-the-meter or distributed system, you're probably trying to size the system to meet an electric load, for instance. For either distributed or utility systems, you're probably basing some of your decisions on the particular utility rate and metering type that your system is eligible for distributed systems, or the PPA price and time of delivery factors that you might be receiving if you are a utility scale system. But those inputs on the other side are balanced by several different constraints or requirements. So particularly for rooftop systems, for instance, you might have some space constraints. On the utility side, there might be some type of interconnection requirements that you have to adhere to for your system to get connected to the grid. Budget constraints are obviously a big factor. Otherwise, we'd all just be building the biggest systems that we could. And then there's also some constraints from the electrical layout itself, and so I will go into those a little bit more. To start with, let's define some of the metrics, and so this may be a little bit too simple for some of you that are listening in, but bear with me as I briefly walk through some of the things we're going to be talking about. So probably the biggest metric that you're used to hearing when you think of a PV system size is what in SAM we call the nameplate capacity. And PV systems in particular are sort of tricky because they can be rated either on the DC capacity, so the capacity of the modules themselves, or the AC capacity, which is the capacity of the inverters. And those two are not necessarily the same, which leads us to the DC to AC ratio. So you're looking at the ratio between that DC capacity and the AC capacity of the inverters. So in SAM, when we say nameplate capacity, we're referring to the DC capacity of the system. But just so you know, other people could be referring to the AC capacity when they're talking about a system size. And then down below the pictures, you see the things that actually control the different sizes of a system. So we're looking at basically 3 variables, which are the number of modules that you have in a string, so modules in series, the number of strings that are in parallel, and then the number of inverters. And I'll get into these in SAM a little bit as well. One point that I want to make before I jump into SAM is about the DC to AC ratio itself. And this is a point of frequent confusion, especially when people are trying to use automatic sizing in SAM, which I'll show as well. But the DC to AC ratio is not a continuous set of options. For any given system, you are looking at actually a discrete set of options, which are limited by the PV panel size of the PV panel that you've chosen and the inverter size, right? Because those are discrete objects. You can't have half a PV panel or a third of an inverter. And so I've given an example here where we're trying to make a system size that is an 8 kilowatt system, and we have some 200 watt panels. So fortunately, that divides nice and easily, which is why I chose it. So 40 modules will give you exactly an 8 kilowatt DC system. But then the trick comes with your inverter. So let's say you're getting the best deal on an inverter that is 3 kilowatts. Well, for an 8 kilowatt system, you can either choose to have 3 inverters, so the situation on the left, which will give you a DC to AC ratio of 0.89, or you could choose to have 2 inverters, the system on the right, which gives you a DC to AC ratio of 1.3. And so if you're aiming to get to a DC to AC ratio of 1, these are actually going to be your 2 closest options, and you'll have to pick between those. This particular phenomenon becomes more of a problem for smaller systems. Once you get into really large utility scale systems, you can get pretty close to the desired system size and the DC to AC ratio, just because you have more options with the number of components, right? Because the size of the inverter is a much smaller percentage of the size of your system. So with that sort of brief introduction into the world of PV sizing, let's jump right into SAM. So I have SAM open here, and I'm going to go ahead and start a new project in the detailed PV world. And I'm going to be doing all of my demos with the detailed PV model because the simple PV watts model doesn't assume real components for modules or inverters. So it assumes that if you specify a 4.63 kilowatt inverter, that could potentially exist in your world, whereas in the real world it probably doesn't. And so that's the reason I'm going to be using the detailed model, because then we will be working with the types of constraints that cause PV sizing issues. And I'll just go ahead and choose a residential model to start. And then along the left here, I'm going to skip right down to the system design page. And let's take a look at what we have here. So to start with, if you've never sized a PV system before, this can be a little daunting. But you'll remember that I mentioned that there are 3 numbers that sort of control the size of the PV system, and those are listed over here. So you have the number of modules per string, which are wired in series. You have the number of strings in parallel, and the number of inverters. And before I get into the actual SAM implementation, let's look a little bit at how those numbers are important for your system. So you can see in the next section, the configuration at reference conditions, that we have a whole host of calculated metrics here. And they might be confusing, but they are intended to actually help sort of clarify your system a little bit. And so let's start with the number of modules per string. And let's see how that affects your system. So I'm going to point to these calculated values down here. You'll see the string VOC, which is the open circuit voltage, and the string VMP, which is the maximum power voltage. And so these two numbers are a result of how many modules you have in a string in series. So if I, for example, change this number to 6, the number of modules per string, you can see that the string VOC and string VMP changed. And that's a pretty simple calculation based on the module specifications themselves and the number of modules in a string. Now, why does that matter? Well, if you look over here, we also have some inverter specifications. And you can see that two of the things listed here are the minimum MPPT voltage, maximum power point tracking voltage, and the maximum power point tracking voltage. And so the reason that your string voltages are important is that you need them to be within the inverter's specified MPPT range in order for the inverter to be able to be most efficient and to be able to track the maximum power point of your modules. And so if I were to, for example, change this to 8, you can see a new warning popped up in this sizing messages box that tells me that the string voltage exceeds the inverter maximum MPPT voltage. And so you can see that pretty easily right here. Here's the string VOC is 543, and that is in fact greater than the 480 that the inverter specifies. So I'll bring this back down to 7 so that we're not exceeding that. But that gives you an idea of how the number of modules per string affects your system sizing. If we then look at the strings in parallel, what happens if I change this to 3? Well, you can see that the number of modules, obviously before we had 7 modules in a string and 2 strings, it used to be 14 modules, now it's 21. And so that's controlling the DC capacity of my system, is basically how many strings that I have in parallel. The other thing that it's controlling is then the DC to AC ratio, because I didn't change the number of inverters. I now have more DC capacity compared to my AC capacity than I did before. And you can see that SAM reports that here with what your calculated DC to AC ratio is. And so I'm going to pause here to comment on sort of the usefulness of these numbers. This is a beginning place to start to help you appropriately size a system. There are some things that it doesn't take into account, and one of the biggest things is that the ratings that are pulled here for the modules and the inverters are specification sheet ratings based on standard temperature, standard test conditions. So it's a temperature and a radiance. For modules, for example, that's 1,000 watts per meter squared and 25 degrees C. But your voltages can vary actually based on the operating conditions of the system. But without running a simulation, SAM doesn't know what that variation is going to look like, so it bases all of this sizing guideline on those STC values. So that's one example of a limitation, but it is a useful starting point. So now that we have a little bit of a better understanding of what each of these 3 inputs is actually doing, let me then move back into the world of SAM and let's talk about these 2 different sizing options. So by default, when I pick a residential PV system, it's specify modules and inverters is what's selected here. So that's letting you input each of those 3 variables. But if I were to switch over to specify desired array size, this switches SAM into a mode where it does its best to automatically try to get a system that matches your specifications, sort of coming more from the top down than the bottoms up. So you remember when I defined some system metrics, these were 2 of the 2 on the top. So we have the desired array size, remembering that SAM works in nameplate capacity being DC, and the desired DC to AC ratio. And so what SAM does is it basically takes the module that you've specified and it tries to determine the number of modules that you should have in a string by aiming for the middle of this maximum power point tracking range specified by the inverter. So it keeps adding modules until it has hit what it thinks is as close to the middle as it can get, and decides that's how many modules per string. So you can see here, it has calculated that you should have 6 modules per string with this module and inverter that you've chosen. And then it changes the number of strings in parallel to try to best match what you've specified for a desired array size. And so you can see here, this is a pretty good example actually of how this algorithm doesn't do a great job. It has calculated that you should have 6 modules per string and 1 string, which will give you a 2 kilowatt system, even though you specified that you would like a 4 kilowatt system. And I do like to point that out because this is just a starting point algorithm. It is certainly not perfect, and the smaller of a system you're trying to build, probably the weirder configurations this algorithm is going to calculate. So for like a 25 megawatt system, it usually does a pretty good job. For a 4 kilowatt system, it struggles a bit. So that's my warning, is to use these as a starting point, but typically, especially with pretty small systems, you want to take a look at what it's calculating, 6, 6, and 1 in this case, and 1 inverter. And then you might want to go over here and say, okay, sorry, it's 6, 1, and 1. And take a look and say, okay, that's giving me this DC to AC ratio of 0.53. That's not at all close to what I want. What happens if I put 2 strings in parallel? Oh, look, now my system is more like 4 kilowatts, and my DC to AC ratio is a little bit closer to the 1.2 that I wanted. So that can be a pretty normal part of the process in SAM. It is something we're hoping to improve at some point, is the way that that algorithm works, but it is on a long list of desired improvements in SAM, if we put it that way. So you can also see that this can be a little bit of an iterative process. Perhaps you are trying to find the right number of modules to get you to a specific nameplate capacity or to a specific DC to AC ratio. You might try different numbers of modules per string and say, oh, okay, my system is a little bit bigger than the 4 kilowatts that I was interested in, but my DC to AC ratio is closer to the 1.2 that I was hoping for. And so you might not be able to strike a perfect balance between those, which leaves you choosing whether the exact system size is more important to you or the DC to AC ratio is more important to you. So remembering that all of this was using rated values at standard test conditions, the next thing that you should do once you've sort of honed in on a system design size would be to run a simulation and take a look at how your system size is working. So one of the places that I'm going to show you for some of the most relevant information talking about system size is on this losses tree. And so you can see that there's 2 different places here that give you an indication of how your system is interacting. This one, we have the inverter maximum power point tracking clipping. And then we have farther down here, inverter power clipping. And so basically these 2 losses, you can see they're pretty low for this system, so I maybe did a pretty good job of sizing it. But to give you an example of what those 2 inputs are meant to tell you, let me first say something like 9 modules per string. And you can see I get this warning again where the string voltage exceeds the inverter maximum rated voltage, which is even worse than exceeding the MPPT voltage, because that actually can void your warranty for your inverter. And if I click simulate again, you can see that my inverter power clipping increased. So that is saying that the inverter actually couldn't handle the amount of power that was coming from your system. And so this is one way that you can start to get into the process of seeing how your system behaves in real-world conditions, because this has run the actual weather file for your location and figured out what the effects of the system sizing are going to be under those actual real-world conditions instead of standard test conditions. So, Another option that I haven't talked about yet, but is possible for trying to change how this system design could work. Let's say I really want 18 modules, but I can't seem to figure out a way to make 18 modules work with one inverter. Well, I could go pick a different module. So far we've been assuming that you're pretty fixed on your module and your inverter, but if you're not, if you're still in a design phase, you could go up and take a look at your module options and see if you can find a different module and inverter pair that behaves closer to what you're looking for. This can also be a problem if you are looking at very small inverters. Some module and inverter combinations, there actually isn't a number of modules per string that results in string voltages falling within the inverter MPPT. So you could imagine 5 modules per string has a voltage that's too low for the inverter range, but 6 modules per string has a voltage that's too high for the inverter range. In that case, you would almost definitely need to change the module or inverter that you were looking at. And so one of the probably easier ways to do it from a sizing perspective, if you're using the databases that come with SAM to just search for some modules, is to look at the library up here, and you'll see that there's not just the name, which is what they're typically sorted by, but there are other characteristics of the module listed here as well. And you can actually sort by some of these different module characteristics. So if I were to, and same thing for the inverter, if I were to go to the inverter page and let's say I want to look for something that has a slightly higher power than the one I'm currently using, well, I'll go ahead and click on the power here, that's the AC power at reference conditions, and I'll see I have a whole bunch of options for, sorry, I scrolled too fast, 3,800 watts. But let's say I want a bigger one. Maybe I'll pick a 5,000 watt or a 5 kilowatt inverter. I'm just going to sort of randomly pick one. And then if I go back to my system design page, you'll see that my DC to AC ratio changed. And in this particular instance, I didn't go quite big enough that 9 modules per string was allowed. But you can see how if you go sort of back and forth in that process, you could find an inverter that would allow 9 modules per string, especially if you are actually looking by the voltage category of the inverter as well. So knowing that my string voltage is somewhere in the realm of 600 watts, if I were to look for one that had MPPT voltage ranges that included 600 watts, and those are listed down here in some of the reference characteristics, then I could find one that better fit my system. So with that sort of primer on system design and sizing in SAM, I'm going to switch back to the presentation just for a minute to talk a little bit more about selecting a DC to AC ratio in particular. So we're well entrenched in the realm of electrical considerations here. But the DC-AC ratio can be a little bit confusing, and so I want to go into that a little bit further. And the one thing that I want to emphasize is that your ideal DC to AC ratio isn't always going to be 1. And there are a lot of different considerations that can go into what you might want your DC to AC ratio to be. One of those could be a price difference in inverter sizes. So for example, let's say you have a 4 kilowatt DC system. You could look for a 4 kilowatt inverter, but maybe you find that a 5 kilowatt inverter is a more common size and it's actually cheaper than a 4 kilowatt inverter. That might cause you to pick a DC to AC ratio of 4 to 5 or 0.8 instead of the 1 to 1 that you were thinking about, just for cost reasons. Another consideration is your inverter efficiency or the inverter's DC rating. So it could be that you have found an inverter that's pretty cheap that exactly matches the size of your 4 kilowatt system, but maybe its efficiency curve doesn't quite do what you want it to do, or maybe for a very small system you wouldn't want to pick a very large inverter because then you'd be down you can see this is an inverter curve in this screenshot here, showing the efficiency of your inverter compared to the rated output power. And if you have a pretty small DC system compared to what the inverter is actually rated for, then you end up in the part of the curve that really isn't, the inverter isn't nearly as efficient as it is anywhere farther up in the curve. So that would keep you from way oversizing your inverter, for instance. There's another consideration for selecting your DC to AC ratio, and that could be the degradation of your modules. So over the lifetime of your system, your PV modules are going to degrade at some percentage per year. The default assumption in SAM is, I believe, 0.5% per year currently. And so you can see in this plot here that you're looking at the energy over the lifetime of the system, and it's decreasing as the system goes forward. So each year the modules are actually producing slightly less power than they were the year before. And so if you have an inverter that was sized to handle all of the power that the panels produced in year 1, by the time you get to year 20 or 25, your inverter might be actually a little bit oversized. On the flip side, if you have your DC system in year 1 produces a little bit more power than the inverter can handle, by year 25, they might be sort of a better match. And so flipping back to SAM for a minute here. Bear with me. There it is. I want to, at this point out one of the other things that can be important in looking at the sizing of your system, which is which way you choose to run SAM as far as the lifetime is concerned. So a couple of years ago, we added the capability, instead of just running the PV system simulation for 1 year and then extrapolating how those results would look for the lifetime of the system, you can actually run the simulation over the entire analysis period. Now, the advantage of this is that it allows every year the degradation can be taken into account on the DC side, so the amount of DC power you have will change, and then that will affect in that year the inverter's efficiency, so how it handles that DC power. And you can see if I run this simulation here, it takes slightly longer but not too bad. And if I go over to the time series graph and I look for my DC power and my AC power, which could take me a minute to find in this long list of variables here. Here we go, array DC power and system power generated, which is AC. This is showing for 1 year. You can see that there's a little bit more DC power being generated than the inverter can handle, so the inverter is clipping it. But if I zoom out to look at more of the system lifetime, you can see that the clipping is pretty bad in year 1, but by the time you get in here, the DC power has degraded enough that the inverter clipping is not as bad. And so this is one of the advantages of the lifetime mode, is it does allow you to look at the effect of degradation on your DC to AC ratio throughout the lifetime of the system. And one other set of outputs that I would like to point out here for how to look at those clipping losses is in the data tables. So if I search here for clipping, or just the word clip at this point, you can see that we have a handful of outputs that help you understand what your system is doing with the DC to AC ratio that you have. So you can take a look at what the power clipping loss is, or you can look at it on an hourly basis as well, the power limit versus the MPPT limit. And those are explained a little bit more in help as well, but basically one is limitations by the fact that you're not within the maximum power point tracking window for your string voltages, and the other one is clipping due to the fact that the overall system size is just bigger than the inverter can handle. So you can also take a look at those on an hourly basis. So if for example, I were to go to the system design page, and let's say I specify a 10 kilowatt system with a crazy high DC to AC ratio. You can see that now there is some clipping, whereas before there wasn't. So this helps to give you an idea of what your system is doing with the sizing that you've picked. Now, all of this can get a little bit confusing, so I also want to be sure to point out the macro that we provide to start to help clarify that information a little bit. So for those of you potentially not familiar with macros, these are additional features. They're sort of analogous to like a macro in Excel, for instance, where you can run some code that will perform a certain set of functions. And so we have used SAM's built-in scripting language to write some macros that provide extra features that we think are particularly helpful. And you can do the same thing if you are a coder or a scripter, is write your own macros for features that perhaps people in your company are interested in, or you just want to look at a certain analysis frequently. But one of the things we have here that we ship with SAM is an inverter sizing information macro. And so this tries to help you get a little bit more information about how the sizing of your system looks over the lifetime of your system. And so I'm just going to go ahead and click Run Macro because that's probably the fastest way to show you what it does. You can see it pops up this window here with some information. So it talks about the DC to AC ratio and how that changes throughout the lifetime of the system. So you can see that, as I mentioned, the DC to AC ratio in year 1 versus the DC to AC ratio in year 5 are effectively actually a little different because the modules have degraded. So that's why this is labeled the effective DC to AC ratio, because it takes into account that degradation instead of just the nameplate capacities. And we also have in year 1, I didn't point out, but over here there are options for a couple of additional inputs to the macro. And so you can also take into account light-induced degradation, which is an initial hit that the modules take as soon as you put them out in the sun. And that can even cause a difference between your nameplate DC to AC ratio and what you're actually experiencing in year 1, although it is a fairly small difference. The macro also helps to sort of summarize some of your clipping information. It can tell you the number of hours that are being clipped by the two methods that I mentioned. So either you're outside of the maximum power point tracking window, or you're just well above what the inverter can convert. It will give you an idea of the total energy that you've lost and percentages, so on both an absolute and percentage basis, what the energy that you've lost due to clipping is. And then it can also give you a little bit of a summary of what types of voltages your system is experiencing, not just at STC, but throughout the real year that we've now simulated. So it reminds you what that MPPT window is for your inverter and what the maximum inverter voltage is. And then it shows you throughout the whole year what was your actual minimum and maximum voltage, and helps you see how those compare to your inverter window. So this is, again, under the real operating conditions rather than just STC. And I will also mention that one of our colleagues is currently working on updating this macro to provide more useful information, and we are very excited to see that improvement hopefully come out with a soonish version of SAM. So be looking for that as well. He's done lots of great research on figuring out a little bit more what types of information he could give you in this macro here. So now that I've really thoroughly gone through that system for sort of your normal central inverter situation, I'd like to switch over and just briefly touch on modeling systems with microinverters or DC optimizers, which are a little bit different than a central inverter system. So I'm going to leave the default module that was selected in here for now, and I'm going to, like I mentioned, look for a microinverter. So I'm going to sort this by the total power of the inverter. and then go find the smallest inverters I can, and look at that. There's some microinverters here. So because my actual module was a 335 watt module, I'm going to guess that a 175, oops, reset my preferences here, 175 watt microinverter probably isn't going to work. So I'm going to go a little bit bigger than that. Boy, we have a lot of inverters in this list. Still going. Here we go. All right, something in the realm of a, oh, those are, here we go. How about one of these microinverters here? Just because it matches up with a little bit better with the module I've specified. So now if I go back to my system design page, I'm going to go into the world of specifying modules and inverters because as I mentioned, the automatic sizing algorithm is not great, and it is even worse with microinverters. And so here, the way that you're going to want to do this is basically you can imagine that each module is wired to its own small inverter. Imagine that. That's why it's called a microinverter. So you're going to be looking at effectively one module per string. Some microinverters are actually wired so that you have two, you can connect two modules to them, so you might put two, but typically it's going to be one. And then you would just want to specify the number of strings in parallel that you have. So let's say maybe 10 strings in parallel, which gets me into the realm of a 3.5-ish kilowatt system. And then, because I have one module per string, or one module per inverter, I'm also going to need 10 inverters. And so this is how I would set up my system to tell SAM to run in such a way that it correctly is modeling how the microinverters and the panels are wired. And now you can see that I did a bad job of selecting my module and inverter because I have all these extra warnings in my sizing system here. So my DC to AC ratio is 1.12. That's not terrible. But you can see that SAM has calculated there is no number of modules per string that results in both the string VOC and the string VMP being within the inverter MPPT range. And so I take a look at this and I see, oh yeah, there's my string VOC and string VMP, and look at that, they definitely both exceed the inverter MPPT range. And this MPPT range is sort of narrow, so I might actually have trouble achieving string voltages that fall within this range, which is why SAM is giving me the warning. So this would be an example of an instance where I would want to go back and pick a different module or a different inverter to get rid of that warning and find something with string sizing that more accurately fit the inverter MPPT window. But for now, I'm not going to do that, just in the interest of time. And I am going to pretend that that system were actually okay and move over to the losses page, which is the next thing to take into account for systems with microinverters. And you can see that there are several phenomena that we don't explicitly model in SAM. We just account for them using a percentage loss. One of those things in the case of SAM is the module mismatch, the DC wiring, etc. And the defaults here are for central inverters. And so if you're using a microinverter, chances are that you don't have any mismatch loss because you don't have multiple modules to have mismatch loss with each other. So if I click this button to set the defaults for microinverters instead, you can see that the mismatch loss goes to 0. Now, a similar functioning piece of equipment, but not quite the same system, would be DC optimizers. So for DC optimizer, you wouldn't set it up necessarily like microinverters. You would set up your system as normal. But you would want to make sure to come to this losses page to set losses that were appropriate for a system that has DC optimizers. So you can see when I click this button, it adds a little bit of a power loss associated with having the DC optimizers in the system, but it keeps the module mismatch at 0 because DC optimizers also serve that function where they decrease the mismatch in your system. And I do want to point out that pushing the string inverters button will bring you back to the default losses, and that really should say central inverters. We labeled these buttons before string inverters had really become apparent and become a thing. String inverters and central inverters are likely to have fairly similar losses, although a string inverter might have slightly less mismatch or potentially wiring losses or things like that. But we don't have a button for that currently. So this string inverters button represents central inverters, and I have made a note to change that in a forthcoming release. So now that I've covered microinverters and DC optimizers a little bit, I want to go back to a string and central inverter and demo one of the last phenomena I want to talk about is multiple subarrays. So I'm just going to go ahead and start a new case here, another residential case, and go back to the system design page. And now subarrays are sort of a strange concept. What we mean in SAM when we say you have different subarrays is that a subarray is a group that shares all of these characteristics. So they have the same type of tracking system, which in our case is just fixed tilt. They have the same tilt, they have the same azimuth, they have the same spacing. So you could imagine in a sort of small residential system, for example, you might have one set of panels on the east face of a house and one set of panels on the west face of a house. So what you would want to do to model that in SAM is you would want to put that in a separate subarray, because suddenly you have another group of panels that all share characteristics, but they are not the same characteristics as the first group. So let's say that they're both going to be fixed tilt, but one set of panels is indeed on the east face of a roof, so it's facing 90 degrees is east in SAM, and the other one is west facing, so 270 degrees in SAM. But we'll assume that they both have the same tilt. And then you would simply set it up like that. You can go ahead and click Simulate, and you will get the output for the combined system. But if you look in the detailed data at the hourly data, you will also get outputs for subarray 1, a whole host of them, and separate outputs for subarray 2. So if I were to look at, what's a good thing to look at here, the nominal plane of irradiance for each of those two subarrays. There we go. You can see that they're different. And it's sort of surprising that the one is 0, and perhaps I messed something up. But we would expect them to be a little bit different because one's facing east and one's facing west. So that is just to give you an idea of how you deal in SAM with a system that has a couple of different sections that all share these qualities but are different from the rest of the system as far as the tilt or the azimuth or the spacing or even the tracking type. The very last thing I want to touch on before I open it up for some questions is just a quick note on the actual physical sizing of the system. So SAM doesn't do a whole lot of physical modeling of the system. It's not really its intent. But we do give you a couple of indications of what an estimated module area might be. So that's based on the module itself. So it has a specification for an area. And then the land area, which in this case is very small because it's a very small system. So it's not really registering on a scale of acres. But for a very large system, it could give you an estimate of what the total acreage that that system might take up would be. The only time that SAM does start to care a little bit more about the physical layout of the system is when you are looking at either shading or snow losses. And so that's when I would come over to the shading page, and I'd see here are a couple of more inputs than we usually have to specify for SAM. So if I were to enable self-shading, for example, you would see that I have to specify how the modules are actually laid out in rows, because the front row would be shading the next row, would be shading the next row, etc. And I would also have to give the aspect ratio of the module and select whether they are laid out in portrait orientation or landscape orientation, so whether they're tall or long as far as how you've laid them out, because that all helps SAM calculate what the dimensions of these rows are, which then affects how much they're shading each other. And in the realm of snow coverage, which also needs those inputs, it helps determine how many modules are covered with snow as the snow is melting away. So you can imagine if snow melts off half of a row in a day, it matters whether that row is only 1 module tall or 2 modules tall. So that sort of goes through the different things that I wanted to demo in SAM. And I just want to conclude with some of the limitations of SAM for sizing. So SAM does not perform a full electrical model. It doesn't show you frequency effects, and it does not properly model what the inverter and how the inverter would be controlling the modules if you are outside of the MPPT range. So those don't enable perfect sizing using SAM. It also assumes that the grid can handle any level of power that's created for the distributed system models. So it doesn't, for instance, model any interactions that the grid has with your system. It doesn't outright calculate wiring losses. It just has you put them in as a percentage. And it doesn't model standalone systems. And you also may have noticed that this webinar did not at all deal with sizing for PV systems with batteries. That's definitely outside of the scope of 1 hour for sizing. So maybe someday we will have a PV and battery sizing webinar dedicated just to that. So with that, I've gone through a lot of the different sizing topics that can be relevant for PV system design in SAM, and I'm happy to open it up for questions.
Thanks, Janine. There is one question here about using the GCR to about finding the optimal GCR for a limited either a roof space or ground space.
Okay. Let me flip back over to SAM for a minute here. Optimizing GCR for limited roof space or ground space. So I guess for that one, you would have an idea of what your total area would be. So why don't I switch this to a pretty big system so that it actually registers. We'll look at a 25 megawatt system instead. And you can see that now SAM has calculated that that will take up about 100 acres with my GCR of 0.3 here. So if I change my GCR and I put the modules a little bit closer together, you can see that it only takes up 60 acres. And so this is just a straight conversion. In fact, you can see what the conversion is over here. It's written out in this nice little help tidbit here. So what you might want to do actually would be to use SAM's parametric feature, which lets you select an input, and in this case I might pick ground coverage ratio. And you can take a look at how changing the ground coverage ratio, for instance, from 0.5 to 0.4 to 0.3 or whatever I'm interested in, you can see what effect that would have on your annual energy, for example. And to do this correctly and actually look at that effect, I would want to make sure to have enabled my self-shading, right? Because that's when the ground coverage ratio starts to matter, is if the system is shading one another. So I do have it enabled here. And I would run some simulations, and obviously I didn't do a real bang-up job of this. So you can see how that ground coverage ratio is affecting your annual energy. Sort of like we might expect, the further apart you can space your panels, the higher power output you'll get. But then you could basically set yourself a limit by using this type of equation. So what is your maximum area and how does that translate into a maximum ground coverage ratio. And then you could use that one to see what your annual energy will look like with that specified ground coverage ratio. Anything you'd want to add on that, Paul?
Yeah, just to mention the land area and costs, land cost on the system cost page. So if you're looking at this question in the context of a large ground-mounted array, that you can account for an estimate of the land cost using those inputs.
Good point. Thanks, Paul.
Somebody wanted to see the last slide you showed with the main features and limitations of SAM.
All right.
And there was another question. There's been a couple of questions about negative output values and inverter consumption. Might be worth taking a minute to show the inverter consumption inputs on the inverter page, and then to show the inverter consumption in the results.
All right. So as Paul mentioned, the inverters list a bunch of different specifications, I suppose. And one of the ones sort of hidden partway through here is the power consumption at night for that inverter. So for the residential inverter, you can see it's pretty small. But if I were to look, for instance, at a utility scale system where you have several inverters all drawing a little bit of power at night, their power, because they're bigger, their power consumption is also bigger, the order of 300 watts instead. So if I were to just simulate this default system just to show the effect, and I look in data tables, I'm going to look for the hourly system power generated. And as Paul mentioned, the value at night is this constant negative value. That is a direct result of those inverter power consumption. So you would have the inverter power consumption specified here, and it ends up getting multiplied by the number of inverters that you have in your system. So they consume more power the more inverters you have. And that's what gives you this negative system power at night. And I am not remembering, yes, there is also a loss in the loss diagram that shows you as a percentage what that nighttime consumption is. So you can see that even though they look like a pretty big value, it ends up being a fairly small percentage of your annual generation, just because in this case the system is so huge. And then you can also look specifically at the nighttime losses. And you can see here, one thing that's helpful to point out is that the nighttime loss from the inverter is actually slightly lower than the negative power generated. And so you might be wondering why that is. The answer is that you end up with wiring losses going in the other direction when the inverters are drawing power. So they're actually drawing an extra bit of power to account for those wiring losses.
Okay, we've got a few questions about shading, which is a little outside the scope of this presentation. But here's one about inverters that's somewhat related, I think, on the inverters page, why there are some inverters with 240 volts and some with 208 volts. Seems like maybe that's the module.
This is one of those. Steve has a thought on that.
Okay.
Go ahead, Steve.
No, Okay, I mean,
Oh,
typically for a residential house, it's 240 volts, but then when you go to the 208 or 480 volts, it sometimes goes to a larger facility and a three-phase type wiring system, but no definite answer on that.
okay, let's see. So here's a follow-up GCR question. How do you cap land area when optimizing GCR? So you could find the optimal GCR for a given roof area. There isn't a way to constrain SAM for a given roof area or ground area. So you kind of have to run the model iteratively and try different GCRs and look at the resulting areas to do that kind of manually.
In general, though, the farther apart your modules, the more power you're going to produce. There isn't some type of parabolic curve as far as row spacing is concerned. So basically, the optimal system, just from that respect, is going to be at your maximum row spacing within a given system size. But if it causes you to change system sizes, which is what I imagine you're getting at, then there is probably some type of balance between system size and spacing. And as Steve pointed out silently over here on the end of that question was being asked, probably the best way to do that would actually be to use SAM's built-in scripting language, LK, to write a simple script that runs that type of analysis and can, in scripting, you could set a maximum land area and check against that maximum for each system size. And that would allow you to enforce certain conditions and then loop through several different system sizes and ground coverage ratios to find what the optimal would be.
And there's a question here about how the 3D shade calculator and self-shading calculator interact. I think we can just make a quick note that they're two separate models, so they don't really interact. If you're using the 3D shade calculator to model row-to-row shading, which is possible, then you'd want to be sure to turn off the self-shading model here, so you're not duplicating that estimate.
And it also might be worth demonstrating that we have all of the previous SAM webinars on the SAM website, which is just sam.nrel.gov. Over here under resources, webinars, and I believe that there is an older webinar on using the 3D shading model, and if you scroll through you can find a little bit more detail on some of that somewhere probably. As well as a webinar that talks about getting into using the SAM scripting language, which I know I mentioned as well.
All right, I don't see any more questions. So I think we can call it a day. Thank you, Janine. If you have questions for us, please feel free to contact us on the support forum or using the contact page on the SAM website. And again, we'll be posting a recording of this webinar along with copies of the slides that Janine used on the webinars page, probably later today or tomorrow. Thank you very much for participating, and we look forward to hearing from you sometime soon. Goodbye.